Hello, I'm Malcolm, a software engineer at Eventual. Today, I'm going to show an in-depth tutorial of how you can use Daft to construct a feature-rich PDF processing pipeline. I'll show you how you can use Daft to download PDF files from an S3 bucket, extract text boxes by either using OCR or a commonly used PDF processing library, organize this extracted information into custom-defined Pydantic classes, perform spatial layout analysis to group text boxes into lines or paragraphs, compute embeddings using a model running on the GPU, and finally, to save everything using Parquet. Now, without further ado, let's dive into the tutorial. Before we see any code, let's install Daft and all the dependencies we'll use here. As you can see, we've already had this loaded up, nice and cached, and we have all of our libraries coming in. Now, we also test this tutorial with our CI system, but we won't need to use that here today. And to make our lives a little easier, we'll just define all of the imports that we're going to use throughout the tutorial notebook here. First, let's get our S3 URLs for all the PDFs that we'll use here. As you can see, we'll define an IO config that we'll use to access this publicly accessible bucket, which is why we have the anonymous is true mode here. And at first, we're just going to get a sample, so we'll get the first 10 PDFs, or URLs to look at. Now, when you have a data frame in Daft, you can do a lot of operations on it. But if you're exploring, I'd like to point out that you can use the show method on the data frame. This doesn't materialize the entire data frame. Instead, it only does enough computation to show us the first 10 rows. This is what it looks like now when you just do the initial read from S3. We can see we have 3 columns, the path, the size, and the num rows. We don't have num rows here because we just have files, and the size shows us how large these files are in bytes, and the path gives us the entire S3 key to the PDF. So you can see, here's one, and here's another one. Now, when we want to download these PDFs, we can actually make use of built-in operations in Daft. On here, we can actually use the URL and download methods on the path column. What this does is it actually tells Daft to interpret these as URLs and then use any IO configuration or protocol handling to understand where the content is and download it. Now, if we run this, we actually see that we can download this quite quickly. Actually, these 10 PDFs happened in less than a second, which is great. So if we look at this data frame now, we can see that we've added a new column. It's a binary column, and we're calling it PDF bytes. This is the actual entire content of each PDF file. What we can do now, we have our paths, we have our PDF bytes. Now we should start, before we get into our pipeline, adding a little bit of structure. Documents are very complex objects. Unlike an image, they have usually nested structure. They have things like pages. On each page, we have different elements. Today, we're really just going to be focused on text, but documents can have other things like tables, they can have images, they can have drawings. They can be very complex beasts. So to help manage some of that complexity, what we're going to do is use Pydantic, which is a great Python library, to help us define some data classes that'll keep it easy for us to both organize and program against this data when we extract it. We're really focused on defining a bounding box type for our text. Unlike traditional NLP, documents are two-dimensional. We really care about not only what the document says, but where it says it. For example, if I'm looking at a form and I see something to fill in right next to the word first name, I could probably guess that it's somebody's first name. Similarly, if I'm looking at an invoice and I see a bunch of numbers stacked up together and they're increasing in value, this might be something like the subtotal, the tax, and maybe the final value. And I can kind of infer this just by where these text boxes live. So let's get back to our code here. Here we're going to define a bounding box. It'll have a top left corner, an X and Y coordinate, and it'll have a width and a height. We'll define a text block, which is our content text, and it's defining bounding box. If we're doing OCR, we'll need to know the height and width of the image, as well as the resolution, which will represent as DPI. Each page will have an index, an associated list of text blocks, and optionally an image size if we're doing OCR. The entire document will represent as this parse PDF object, which will have the path or the URL that we had for the PDF originally, the total number of pages in the document, and a list of these parse page objects. We'll also have some other algorithms later that we'll show doing grouping, where we'll use this text line and this index text block and this process class too. Now that we have our Pydantic classes, we'll need to define a function that will let us easily generate Daft data types from our Pydantic classes. To do this, fortunately, we can rely on a great library called Arrow. This function, Daft PyArrow data type, and its helper, PyArrow data type, lets us recursively inspect the Pydantic base class we have and find an appropriate pi-arrow struct or list type or primitive type. We can do this automatically for any data type and thus generate an appropriate Daft data type. So after we download our PDFs, the next part of our pipeline is to actually load the PDF and extract information from it. This is what we'll define here in our next section. We'll use a concept in Daft called a user-defined function, or UDF. This UDF we define is called load, direct, and parse PDF. It has two modes. One is we can use OCR by using the underlying Tesseract library to actually visualize each PDF page and run it through the OCR model to have it tell us where it thinks text lives. Alternatively, we can actually use a PDF processing library to parse the PDF and ask the file format, where is text written? Now, not every PDF can be actually extracted this way, and sometimes the actual extracted text boxes can be a little weird, but that's what OCR is good at the end of the day. But here, we'll just stick to trying to read the PDF file. So in it, when you make a UDF, you can actually define it as a class and decorate it with this @UDF decorator. Note that we always have to define a return type on our UDF, which is for every single time we invoke its call method, what do we expect to get out? Here's where we're using that Daft pi-arrow data type function. Note that we're actually just supplying it our Pydantic class here. So in this function, in our call method, is where we're actually doing all of the processing that Daft is going to do for us. In here, we actually are providing in a series of URLs and the PDF bytes. This is from our data frame earlier. When we take each one of these series, we're going to take one URL, one byte array of the PDF contents. We're going to use the PyMu-PDF library, which is called fits here, in order to actually open this PDF and start reading it. Now, we can perform OCR on it, or we can actually process the pages using the library to get text box out. We'll show how that works here next. If we're performing OCR, then what we're doing is we're going to rasterize each page of the document, and we're going to send this directly over to our OCR model, getting the text blocks out, and we're going to be able to arrange that into our parsed page Pydantic class, which then we can easily take and put into our parsed PDF Pydantic class. Here's what it looks like to use the PyMu-PDF library to rasterize a page. And here's what it looks like to use the PyTesseract library, which wraps Tesseract in order to perform OCR on this page image. Now, if we're not using OCR, we can just try to read the file format and try to look for all the text in the document. This is what it looks like to do this with PyMu-PDF. Importantly, we're using this extract text with bounding box function that we wrote here. What this looks like is we go into the document, we grab a page, and we ask to get all the text blocks and to get all the lines in all the text blocks, every span, and then every piece of text in each span. It's a lot, but it works. Now, let's actually see what it looks like to perform OCR and extract text from the first PDF in our collection. Although Daft is a great processing framework for large data, it's also great for the small. We can easily take our sample and get the first example out of this, and then just use our PDF processing library to load this up and see what it looks like. Now let's use that OCR document function that we just showed to actually perform OCR and look at the first 25 text blocks we get out. As you can see, this one looks like it has some things that are coming from an email or a memo. We can see to, from, sent, some dates. And if we actually go into the PDF file format and we ask it to read the file and look at the text on the first page, we can see some overlap and some similarity, but there's also some different things that are showing up here. Note that we also have the coordinates of each bounding box, so we could go back into our document and actually see where precisely each piece of text is appearing on the first page. Now that we can load PDFs and format them into our process PDF Pydantic class, we can start to define the steps of our document processing pipeline. Here, we'll define another UDF, which we'll call doc processor. This one will use spatial heuristics to group our extracted text blocks into more coherent and usable groups of text. At the end of the day, we want to embed this text, and it doesn't really help if we embed something as small as 2. We'll also want to make sure that the text is in reading order when we group it, which we'll define here as left to right and top to bottom. Now, this isn't always the case for all languages, but so it's important to know in your PDF collection what languages you're using. This document processing UDF has several configurable options. We can have it only group text into lines, which is using the X coordinates, or we can have it group text into paragraphs using the Y coordinates. By default, we'll have it group into paragraphs. Let's look at what this UDF looks like. So again, it's another class-based UDF. We provide the configuration options to the constructor, and then our call method here is processing each document. We only have a single column coming in, and we're going to take each one, run our page pipeline on it. Our page pipeline is just a simple Python function here. This takes our Pydantic class, a single parsed page, configuration options, and it goes through the following. It sorts all the bounding boxes into reading order, and then groups all of those bounding boxes into text lines. If we're grouping into paragraphs, it also then looks at those grouped text lines and tries to merge them into paragraphs. Finally, we want to make sure that we're going to be able to read the corresponding text boxes in reading order, so it does that. The bounding boxes reading order does the left to right, top to bottom, and this is really looking at each coordinate of each bounding box, the top left, and it creates a small fuzzy region, like a row for it, to determine if it's in the same top to bottom ordering. Within that row, it then can do the left to right ordering on the x coordinate. Similarly, grouping into text lines, what we're doing is looking at each text box and having a small threshold around it. And we ask if there's another text box intersecting that threshold horizontally, then we can group it together. When we group into paragraphs, we're doing the same thing, but we're looking at the y coordinate. If we have two text lines that are within a small region above or below one another, then we group them together. Now that we have nice groups of text, we can generate embeddings for them. We'll define a functor here that makes a UDF from a SentenceTransformer model. The resulting UDF will make sure that the generated values are both of a fixed size and two of a known data type. Here we'll use our classic 32-bit floating point number. This text embedder UDF we're defining here takes our SentenceTransformer model, makes sure that we have a dimensionality, puts it into evaluation mode because we're not computing gradients. What we're actually returning here is this embed function decorated with the Daft UDF decorator. Note that the return type is an embedding type. This is how Daft represents something that is a fixed size and known numeric data type. This looks kind of very much similar to any normal PyTorch code. We're going to enable the no-grad mode, ask the model to encode all the text, get embeddings out, and then we'll use the series from NumPy method. Okay, so we have all the parts of our pipeline together. Now we just need to wire it up. In Daft, we express our entire pipeline as a data frame. We use the data frames methods in order to produce transformations from one view of the data into another. Here, we'll combine all the functionality we talked about in this tutorial into a complete data frame-based pipeline. At start, we'll define all of the configuration options that our pipeline will use. We can change any of these values and rerun this notebook to see how they affect the pipeline. First, let's check some assumptions on our options for the data frame-based processing pipeline. To make things go a little snappier in a tutorial, we just made sure that we limited the first 10 pages of each PDF. You can easily turn this limit off, and you can run on any number of pages on any PDF. But note that your processing times may vary if you have small PDFs, like 1 or 2 pages, mixed in with really large PDFs. So, putting it together, our first step is to enumerate all of the S3 keys. We'll use the Daft from glob path with our IO config that knows about AWS, and we'll go and get the path and size and num rows for everything in our S3 bucket. Next, we'll use Daft's built-in URL download functionality to download each PDF in parallel. Third, we'll use our load, direct, and parse PDF UDF in order to extract text boxes from each page of each PDF. Let's look at this a little bit. Here we're going to use with column. This tells us that we want to make a new column called parsed, and the way we're going to make this is using a UDF, and the UDF is going to take two inputs. It's going to take URL column as well as the PDF bytes column. Now, Daft will actually handle taking the data and supplying it to a UDF, but we need to do this here in order to tell Daft how we're wiring this up. Let's take a little note here to talk about how Daft works. In our above UDF application, we're providing column expressions as input. Specifically, this is what we're talking about when we said call and we gave it a string. When we write something like call of URL, we're telling Daft that this is an expression. It's referring to the URL column. This lets us write expressive code, but still have Daft manage all of the runtime and hard parts for us. In our code, when we have this, load, direct, and parse PDF with init args, we're actually constructing our object. Once we have this UDF object, we can then apply expressions to it. That's what this part is, call of URL and call of PDF bytes. Note that above we combine this all into one line. We can easily break this up into 2 lines and have it be equivalent. Our fourth step is to do text box processing. Now for the fourth step, text box processing. We have already processed the doc.gmbit into our Pydantic classes, and now we can perform the custom logic grouping these text boxes into either lines or paragraphs. We use our doc processor UDF here, and we have a very similar setup. We construct it, And then we apply the column expression that contains our parsed Pydantic objects. If we look at the schema here, we can see something interesting. While the URL we have is still just a UTF-8, which is a string, our process raw column here is actually a list of fairly complex structures. If we look at this, we can actually see that this corresponds one-to-one to the nested Pydantic classes we have. But these are arrow types, so Daft knows how to use them natively. This, though, isn't as useful. It's hard for us to take this representation and ask a question like, what are all the text that appears in the top left of every page? In order to help us answer those kinds of questions, let's go reformat our data. We can use Daft's explode and with column operations in order to help us do this, to unroll and flatten out this complex nested structure. So first we'll take each one of these, and since it's a list, we can use explode to turn this into a new column where we have each individual struct instead of a list of these structs. Then what we can do is we can define two new columns, the page index, and we can also have these index texts. Here we can provide this as a column expression, note that it's a struct, and then access individual fields of that struct. When we get the index text, this is our reading order for the text boxes. We want to explode that as well. This way, at the end of the day, what we have is our original URL, the page index, and each text box as it's coming out. Let's take a little moment to explain the structure access expressions that we used here. Note that we're using this .struct method on the expression to construct something that allows Daft to extract individual field values from our complex document structure. When we write something like column of text blocks .struct.get bounding box, we're telling Daft that we want to access the bounding box field of each element from the text blocks column. From this, we can apply additional field selecting logic. For example, accessing field X to get the value for field X on the bounding box. The last part of our text box processing step is to extract the text and bounding box coordinates into their own columns. We also want to preserve this reading order as an index in our column too. Let's look at this expression. We're going to make a new column called text blocks, and we're going to create that by looking at the index text and getting each text element. Similarly, reading order is the same column that we're extracting, but we're getting the index instead of the text this time. After that, we don't need to use the index text anymore. We can make a new text column by going into each text block and just getting the individual text. This is because that text block also includes the bounding box. And instead of having that be a nested structure, we'd like to put those into their own columns. So we'll define an X, Y, height, and width column. And we'll use the same pattern here, getting the text blocks column expression, treating it as a struct, getting the bounding box, then accessing each individual field. This is what the schema looks like at the end of the day here. We have a URL, page index, the reading order that we can see the text in, the actual text itself, and the bounding box coordinates. And this is in a nice data frame that we're really used to and we can do lots of kinds of processing with. And to show that, we'll use our text embedding UDF function here. Note this is very small. We just have our new column, embeddings, and we're going to construct that by using our text embedder UDF with our model on the text column. If we look at this pipeline now, we can inspect it by asking Daft to show us the final schema, the data frame. Note this looks like we have before, but we have our new embeddings column, which is known here with our embedding of float32 and a fixed size of 384. That's the dimensionality that we're getting out of our SentenceTransformers model. We can also peek under the hood here and ask Daft to show us the entire logical plan that it will run when we ask it to execute our pipeline. On any data frame, you can do this by saying df.explain. This is quite complex, so we'll leave it as an exercise for you to go download the tutorial and run yourself, take a closer look. But if you're a database nerd, this is chock full of a lot of goodness. Now, we haven't actually executed anything yet. This is because in Daft, data frames are lazy. They're only evaluated once it's necessary. There are a few methods on a data frame in Daft that'll actually force it to materialize or execute. A very common one is called collect, but that brings everything in memory. We don't want to do that here. Instead, we're going to use the write Parquet method. This takes our data frame, executes it, and writes it to disk as Parquet, which is a very common column-based storage format. And it's really easy to do this in Daft. It's literally just one line. We have our data frame we constructed, we call write Parquet, give it the output directory, and that's it. It'll materialize and run this without us doing anything else. And that's it. We have our entire PDF processing pipeline in Daft. We were able to use Daft to enumerate our files in S3, download them, get the PDF bytes, and parse them into nice Pydantic classes. We're then able to run some heuristics to group the text into paragraphs, and then we're able to use a custom model running on the GPU to embed the text. And finally, we're able to save everything out to Parquet. If you want to follow along or get this tutorial yourself, go to our documentation website at docs.daft.ai, or get started with Daft today using pip install Daft. Thanks for watching, and I'll see you next time.